This work was presented in IWAP 2021, in conjunction with IPDPS 2021, in May 2021. My name is Kengo Nakajima, the University of Tokyo, and Riken RCCS. Title of my talk is, Efficient Parallel Multigrid Methods on Manycore Clusters with Double-Single Precision Computing. This is a joint work with my colleagues Takeshi Oguita and Masatoshi Kawai. First of all, I would like to thank my sponsors. JHPCN and JCAHPC provided us the computational resources. This is the outline of my talk. I start with the background and overview, including an overview of multigrid methods, previous works, and present work. Then, I talk about implementation of cell C sigma, mainly focusing on double precision code. This is the main part. After this, I overview effects of single precision. Furthermore, I overview works related to accuracy verification, then summarize the talk. Multigrid method is a scalable multilevel method for solving linear equations. In the present work, multigrid is utilized as preconditioner for Krylov iterative solvers. One of the important feature is that number of iterations until convergence is kept constant as the problem size changes. Therefore, computation time is order of n, problem size. Multigrid is scalable, but there are many things to be done towards exascale computing. The parallel multigrid method is expected to play an important role in scientific computing on exascale supercomputer systems for solving large-scale linear equations with sparse coefficient matrices. Because solving sparse linear systems is a very memory-bound process, efficient method for storage of coefficient matrices is a crucial issue. In the previous works, authors implemented sliced ELL method to parallel conjugate gradient solvers with multigrid preconditioning, MGCG, for the application on 3D groundwater flow through heterogeneous porous media. An excellent performance has been obtained on large-scale multi-core Manycore clusters. This slide overviews the target application in the present work. Target application is a parallel simulation code based on the finite volume method, FVM, and it solves groundwater flow problems through saturated heterogeneous porous media. The problem is described by the Poisson's equation. A heterogeneous distribution of water conductivity in each mesh is calculated by a sequential Gauss algorithm, which is widely used in the area of geostatistics. The minimum and maximum values of water conductivity lambda are 10 to the minus fifth power and 10 to the fifth power, respectively, with an average value of 1.0. Each mesh is a cube, and distribution of the meshes is structured as finite difference type voxels. The conjugate gradient solver with multigrid preconditioner, MGCG, was applied for solving derived linear equations. A very simple geometric multigrid with a V-cycle algorithm is applied, where 8 children form one parent mesh in an isotropic manner for structured finite difference type voxels. Incomplete Cholesky factorization without fill-ins, IC0, is adopted as a smoothing operator of multigrid process for ill-conditioned problems. The additive Schwarz domain decomposition for overlapped regions is introduced for stabilization of the block-Jacobi type localized procedure of parallel IC0. Sliced ELL method was applied for storing sparse coefficient matrices, which provides excellent performance of memory access. Finally, the code is written in Fortran 90 with MPI and OpenMP. This slide shows previous results for weak scaling by the authors, using up to 65 thousandths of cores of Fujitsu's FX10. Maximum problem size was 17 billions of degrees of freedom. MGCG with sliced ELL provides excellent performance for weak scaling. In the present work, authors introduced cell C sigma with double-single precision computing to the MGCG solver, and evaluated the performance of the solver, with OpenMP MPI hybrid parallel programming models on the Oak Forest PAX, OFP, at JCAHPC, using up to 2048 nodes of Intel Xeon Phi. Because cell C sigma is suitable for wide SIMD architecture, such as Xeon Phi, improvement of the performance over the sliced ELL was more than 35% for double precision, and more than 45% for single precision on OFP. Finally, accuracy verification was conducted, based on the method proposed by authors for solving linear equations with sparse coefficient matrices with M property. This is one of the first examples of cell C-sigma applied to forward-backward substitutions in ILU-type smoother of multi-grid solver, with double-single precision computing. The effect of cell C-sigma for computing with single precision, FP32, is very significant. Let's go into the main part of the present work. Our target system is Oak Forest PAX, OFP. That is operated by JCAHPC, joint work by the University of Tokyo, and University of Tsukuba. The system is by Fujitsu, and it include more than 8,000 of Intel Xeon Phi Manycore processors. Generally, computations with sparse matrices, such as multigrid and MGCG, are memory-bound, because of the indirect memory accesses. The compressed row storage, CRS, is the most popular and widely used because of its flexibility. In the ELL pack IT pack, ELL, the number of non-zero components of each row are set to that of the longest non-zero entry row of the matrix. This format allows one to achieve better performance for memory access than CRS, but introduces extra computations and memory requirements, since some rows are zero-padded. Sliced ELL is an improved version of ELL for unstructured irregular geometries. Cell C-sigma is further extension of sliced ELL, which is suitable for wide SIMD architectures, such as Intel Xeon Phi. In cell C-sigma, C, chunk size, corresponds to SIMD width, and sigma, sorting scope, is specified according to the distribution of number of non-zero off-diagonal components, at each row of the sparse matrix. This figure describes an example where 4 chunks with chunk size, equal to 2, form a single component. This is called as cell 28. In the present work, cell 88 is mainly adopted for double precision, because each core of Intel Xeon Phi has 5 12-bit vector units. If the FP64, double precision, is adopted for real number operations in the program, C equals 8 is suitable for efficient computations, which extract the performance of Intel Xeon Phi. Sliced ELL and cell C-sigma have been mainly applied to SPMV procedures. This is one of the first examples of cell C-sigma for forward-backward substitutions in ILU-type smoother of multi-grid solver, although preliminary works were done by authors. All meshes at each level are colored and reordered with CMRCM2, using 2 colors. CMRCM stands for Cyclic Multicolored Reverse Cut Hilma key. This slide shows implementations of the forward substitution for sliced ELL, cell C-sigma A, SCSA, and cell C-sigma B, SCSB. Sliced ELL and SCSA are in row-wise sweeping for the outer loops. On the contrast, SCSB is column-wise. Generally, SCSB requires more operations than SCSA. In the present work, both of SCSA and SCSB switch to sliced ELL, if problem size for each thread is less than C, chunk size. In our previous works, multi-grid processes by vCycle were applied as shown in this figure. Multi-grid operations at each level are done in a parallel manner, but the operations at the coarsest level, coarse grid solver, are executed on a single core by gathering the information of entire processes. The total number of meshes at the coarsest level is equal to the number of MPI processes. Moreover, overhead of parallel communication is significant at coarser levels. In CGA, coarse grid aggregation, operations for aggregation and disaggregation of MPI processes, are done at a finer level. If we switch to a coarse grid solver at a finer level, more robust convergence and reduction of communication overhead are expected, even though the size of the coarse grid problem is larger than that of the original configuration. Although CGA provides efficiency and robustness of parallel multi-grid method, problem of this approach is coarse grid problem is solved on a single MPI process. Actually, we have developed further improved versions, such as HCGA and AMHCGA, but applied CGA in the present work. This slide describes the summary of configurations in this part. We evaluated performance of weak scaling of MGCG solvers using up to 2048 nodes of OFP. Flat mode was applied, and only MC-DRAM has been used for the computation. 64 of 68 cores were used, and hybrid 4x16, 4 threads by 16 MPI processes on each node, and hybrid 8x8 have been applied. Maximum problem size was more than 8 billions of degrees of freedom. Elapsed time is measured 5 times, and the best one is adopted. Comparison of CRS, sliced ELL, SCSA, and SCSB were conducted. Each core of Intel Xeon Phi has 5 12-bit vector units. If the FP64, double precision, is adopted for real number operations in the program, C=8 is suitable for efficient computations, which extract the performance of Xeon Phi. Cell C sigma switches to sliced ELL if the problem size is smaller than chunk size for each level, color, thread. Coarse grid of SCS is by sliced ELL. Actually, 20% improvement is expected by SCS over sliced ELL, based on preliminary results. This slide shows computation time of MGCG for hybrid 4x16, with 8 nodes of OFP. Time for smoothing at each of level 1 to level 4, is shown. Cell 88 and cell 128 are applied to SCSB. Generally, improvement of performance by SCSB is excellent. Improvement over CRS is more than 80%, and it is more than 35% over sliced ELL. This figure shows weak scaling up to 2048 nodes with hybrid 4x16. Generally, performance of SCS is excellent. Each of figures shows breakdown of computation time for MGCG solvers, in hybrid 4x16, and 8x8. Time for smoothers and MGCG solver is kept constant as the number of nodes increases, while overhead by communications and that by coarse grid solver are increasing. Overhead by coarse grid solver is more significant in hybrid 4x16, where problem size of for the coarse grid solver is twice as much as that of hybrid 8x8, and only 4 cores are used for the coarse grid solver. This overhead can be removed by adopting HCGA, developed by authors. Next, we would like to consider computing in double-single precision. Mostly, scientific computing has been conducted using FP64, double precision. Sometimes, problems can be solved by FP32 or lower precision. Computing with lower precision generally saves computation time, energy, and memory. Approximate computing is originally the idea for image recognition etc., where accuracy is not necessarily required. It is also applied to numerical computations. Computations by lower precision and by mixed precision from half to quad precision are widely used in various types of scientific applications. But, such computations may provide results with less accuracy. P3D is used for preliminary evaluation, which solves steady-state heat conduction problems by finite volume method, FVM, based on operations of 7-point stencil. It is similar to the target application in the present work. Distribution of thermal conductivity, lambda, is heterogeneous. One layer with different material property, lambda 2, is inserted. Ratio of lambda 1 over lambda 2 is proportional to the condition number of the derived coefficient matrix. The derived coefficient matrix is sparse and symmetric positive definite, SPD. Linear equations are solved by ICCG, conjugate gradient iterative solver with incomplete Cholesky preconditioning. The code is written in Fortran 90 and OpenMP, and CMRCM reordering is applied for thread parallelization. P3D supports FP64, double precision, FP32, single precision, and FP16, half precision, while FP16 can be only applied to preconditioning. This slide overviews the results for P3D. Size of the problem is 128 by 128 by 128, total 2 million unknowns. Problem is solved on a single node of Intel Xeon Broadwell with 36 cores. Lambda 1 Lambda 2 ratio changes from 1 to 1 million. This figure shows ratio of FP32 over FP64 for number of iterations and computation time for ICCG solver. If the FP32-FP64 ratio is less than 1, FP32 is faster. If the Lambda 1 Lambda 2 ratio is less than 10,000, application of FP32 increases number of iterations by 20%, and it decreases computation time by 40 to 45%. If the Lambda 1 Lambda 2 ratio is more than 10,000, computing with FP32 is becoming unstable. Finally, FP32 is slower than FP64, if the Lambda 1 Lambda 2 ratio is 1 million. Actually, results are generally inaccurate for FP32, if the Lambda 1 Lambda 2 ratio is more than 10,000. Next slide shows power consumption, watt, and energy consumption, joule, on Intel Xeon Broadwell, when Lambda 1 is equal to Lambda 2. Blue bar is the value of CPU, while pink bar is that of memory. There is no difference between FP64 and FP32 in power consumption, while energy consumption is proportional to computation time. In this part, we consider two platforms. One is Oak Forest Pax, OFP, with Intel Xeon Phi, described in the previous part. Another is Oak Bridge CX, OBCX, which consists compute nodes of Intel Xeon Cascade Lake. This slide overviews the performance of each node of OFP and OBCX. OBCX provides excellent peak performance, while memory bandwidth is much better on OFP with MCDRAM. This figure shows computation time for MGCG solver of SCSB. Various values of C and sigma from 4 to 2048 are evaluated for both of double precision, FP64, and single precision, FP32. In the present work, all variables, vectors, and matrices are stored in double precision for FP64, and all of them are stored in single precision for FP32. C and sigma are equal in the present work. Time is normalized by that of cell 88 with double precision on both of OFP and OBCX. Generally, effects of different values of C and sigma are small in all cases, while C equals sigma equals 8 for double precision, and C equals sigma equals 128 for single precision, are the optimum choices. Number of iterations until convergence is same for both of double precision, FP64, and single precision, FP32. Moreover, results by FP64 and those by FP32 agree well, and relative error is less than 0.1%. Generally, FP32 is faster than FP64, and ratio of elapsed computation time, FP32 divided by FP64, is 0.70 for OFP, and between 0.55 and 0.60 for OBCX. These two figures show time for MGCG with 8 nodes of OFP for double precision and single precision. Improvement of performance of MGCG solver over CRS on OFP is shown in this table. Generally, improvement of performance by SCSB is excellent, and the effects are more significant in FP32 cases. These figures show the results for hybrid 6x8 with 8 nodes of OBCX. Generally, performance is kept almost constant for all of CRS, sliced ELL, SCSA, and SCSB. CRS is the fastest for double precision case. In both of FP64 and FP32 cases, the performance on OBCX is almost competitive with best cases of OFP. Further investigation is needed for improvement of SCSA and SCSB on OBCX. This figure compares hybrid 4x16 and hybrid 8x8 for SCSB with double precision and with single precision. Generally speaking, hybrid 4x16 is faster than hybrid 8x8, but performance is similar at 1024 and 2048 nodes. This is because of the cost of coarse grid solver with larger number of nodes. Another figure shows rate of improvement of performance over CRS by sliced ELL, SCSA, and SCSB. Generally, rate decreases as number of nodes increases. This is mainly because of communication overhead at coarse level and coarse grid solver. In the present work, sliced ELL is applied to the coarse grid solver. If SCSB is implemented to the coarse grid solver, it is expected that the performance of coarse grid solver will be improved for large number of nodes. These two figures shows breakdown of weak scaling by hybrid 4x16 on OFP, for FP64 and FP32. Another significant problem is that the communication overhead is very large. In the present work, significant communication overhead occurs at coarser levels. This is mainly for keeping the problem size of the coarse grid solver smaller. This problem will be also solved by adopting HCGA. Next part is on accuracy verification. Accuracy verification is important, especially for computation with lower or mixed precision. A lot of methods for accuracy verification have been developed for problems with dense matrices, but very few examples for sparse matrices and H matrices. Generally speaking, processes for accuracy verification is very expensive. Therefore, sophisticated method needed, an automatic selection of optimum precision by technology of AT, auto-tuning, is expected. In the present work, method for accuracy verification of sparse linear solver proposed by authors is applied. This is the overview of the proposed method by authors. We need several additional computations to original solving part. This figure shows the results of accuracy verification by this method for the problem in P3D for double precision cases. Black squares show calculated relative error bound. It is overestimated, and much larger than relative residual norm, blue triangles. New error bound based on the improved method, red triangles, agrees with relative error bound very well. This figure shows breakdown of procedures for linear solver and accuracy verification on a single node of OBCX for 128 cube problem with double precision. Accuracy verification is a little bit more expensive than linear solver. This slide shows accuracy verification of single precision cases. Red line shows relative error between FP32 and FP64 at the bottom of the target geometry. Green triangles show maximum relative error bound of FP32 cases obtained by accuracy verification. These agree well, although accuracy verification failed for FP32, if lambda 1 lambda 2 ratio is more than 10,000s. In the present work, the improved method was applied to the accuracy verification of MGCG solver with SCSB. Two types of the problems are considered. Computing with double precision, FP64, with SCSB is applied. In the present work, parallel version of the code for accuracy verification using MPI has been developed for large-scale problems. In the present work, the minimum and maximum values of water conductivity lambda are 10 to the power of -5, and 10 to the power of 5, respectively, with an average value of 1.0. In the accuracy verification of this part, several combinations were evaluated. This figure shows the relative error bound and residual norm for both of small and large cases. Generally, difference between error bound and residual norm is getting larger, as lambda max lambda minimum ratio becomes larger. Finally, I summarize the talk. We introduced cell C sigma to the parallel MGCG solver for both of single and double precision. Excellent performance was obtained by cell C sigma using up to 2048 nodes of Intel Xeon Phi. This is the first example of cell C sigma applied to forward-backward substitutions in ILF type smoother of multi-grid solver with double-single precision computing. One of the future work is applying cell C sigma to the coarse grid solver. While accuracy verification in the present work is very preliminary, further investigation and development for large-scale problems are needed. Thank you very much for your attention.